we're ready to start. So, thanks to everyone for coming in the day after the banquet. I think you'll be rewarded as a speaker. Yeah, we've got a full day of talks. As probably most of you know, the ML workshop a few years ago, well, first of all, it became a little bit more informal than it used to be, so all of the submissions are extended abstracts. So it's really interesting, more speculative things are allowed. And
we can't hear you.
You can't hear me? Okay.
Can you do the microphone?
There is no microphone. Or is there? Anyway, I could just shout. It works better if I stand here. So. That seems to be off. What about the other ones? How about that? Hey. Okay, yeah, so thanks to everyone for coming. Yeah, as I was trying to say, the program consists of extended abstracts, so some of the work is a bit more speculative than you might have had in a more formal setting, which I think is a good thing. The other interesting aspect of the ML family workshop, I should call it, is it's not just about ML. It's open to any statically typed, strict, type-inferred functional languages, and we particularly welcome contributions from other communities. Maybe we didn't get so many non-ML submissions this year, but last year there was quite a wide range of different languages. Having said that, our invited speaker is going to be talking about Idris, which is not ML, but not that far from the ML family. So, and I think it's quite a good thing to sort of take people slightly outside their comfort zone with the invited speakers, so we get to see some other ideas. Anyway, I'm going to hand it over to Edwin now.
Okay, thank you. Can you hear me all right if I talk like this? Yes. I'm going to do some typing later on, which is challenging. I'm holding a mic, so as long as you can hear me, let me know if I need to shout a bit louder. So yes, thank you very much for having me. Thank you for also coming in on the fourth day after the banquet. I've actually just arrived in Oxford, so I'm fresh and enthusiastic still. So hopefully that'll wake you up as well. So, as Dan says, I'm not an ML programmer. It's quite some time since I wrote an ML program, I'm afraid. But I have, while I've not been programming ML, I have been working on my own contribution to the programming language world. And I guess the ML-inspired and derived language, Idris. So, Idris is a pure functional language. And the syntax, as you'll see, is inspired by Haskell. So even if you are all ML people, I hope you can at least read Haskell. Is that reasonably true of everyone? Yeah, lots of thumbs going up. That's good. So if there is anything that looks a bit weird, please do ask. It should only take a little while, a little bit. So do interrupt me if there's anything that's not completely clear. Now the key thing about Idris is it's not really its syntax or the fact that it's ML derived or Haskell derived, but that it has what I like to call first-class types, so dependent types. So I like to call them first-class types because when we're teaching functional programming to beginners, people who've not encountered functional programming before, we like to say functions are a first-class construct in the language. So you can assign functions to variables, pass them to functions, return them from functions, and so on. So the key idea behind dependent types is that types are first class. Types are things you can pass to functions, return from functions, compute, and so on. So this gives you all kinds of interesting powers, as we'll see. But it also introduces a lot of complications. And as a result, a lot of people seem to feel that dependent types are an incredibly complicated thing. And certainly if you see the whole raft of extensions that Haskell has, I think you would be forgiven for thinking that dependent types are an incredibly complicated thing. So what I'm trying to achieve in Idris is to show you that that's not true. dependent types are a way of simplifying all of this wonderful power you get from the type system. And the goal is not only to, dependent types and types in general are a nice way of expressing what you want the program to do, and therefore reducing the cost, I hope, of writing a piece of software which does what it's supposed to do. But crucially, I would like this to be accessible to developers in general. So it's no good having a really fancy expressive type system if nobody can use it. So this is the goal of the overall goal of the project is to write correct software, be accessible to software developers. But what I want to talk about today is something that we don't talk about quite so much in the sort of pure functional programming, theorem-proving world. And that's, how do you deal with the outside world? How do you write interactive programs that interact with external systems? Those external systems maybe don't behave the way you're expecting, and maybe they're not perfectly well behaved. So how do you handle state, exceptions, I/O, and so on? And how do you get the type system to help you along the way? So the plan is I'm going to show you. Firstly, I'll do a brief introduction to what I even mean by first-class types, just so that those of you who haven't seen it before know what I'm on about, and if you have seen it before, you at least know what the syntax I'm working with is. I'd like to talk a little bit about just working with state machines, and I'm going to work up to an example of concurrent programming. So in the abstract, I promised networks and sockets, but I've talked about that too much in the last couple of weeks. So I want to talk about concurrency instead. I do have the networking example as well, if anybody feels shortchanged by the fact that it's within the abstract, so I'm going to show you that in Brady. But I'm going to talk about concurrency and an implementation of something a bit like session types. Okay, so what do I talk about with, what do I mean when I talk about state machines? Here's the simplest example I could come up with that was at least still vaguely relevant to programming. So imagine you have some secret data store which you should only be able to access after logging in, say with a password or a fingerprint or whatever. So that data store has two states. It's either the whole system state relative to a particular user is you're either logged in or logged out. If you're logged out, there's not a lot you can do other than try to log in, and you might succeed, in which case you're in the logged in state, or you might fail, in which case you're still in the logged out state. If you're in the logged in state, you have an additional thing you can do, which is you can read the secret data. So that's the sort of writing example we're going to use for the first few examples of stateful systems. So to get into that, I'm going to show you things in action. Let's have some programming. Let's actually do some programming. I know it's early in the morning, but let's get the text editor out and see. So apparently this is okay. This text size is okay. So I can probably still make it a bit bigger if need be. So the first thing I want to do before I get into this implementation of this state machine is just show you what the syntax of Idris is all about. So this is if you've seen a Haskell program or an ML program, this will probably look a little bit familiar. So this is a type declaration. So just the function name and its type. So single colon obviously for the type declaration because that's the correct way to do things. So we have just as with Haskell types, you give argument type, an argument type, an arrow, and then the return type. Unlike Haskell, we can give names to the argument types. So it's possible, and we'll see this in a moment, it's possible to use this name later on in the type. We'll see how that works in a moment. Now, what I'm going to do is, I'm going to do this, I like to call this type-driven development. So TDD as in type-driven development. And the idea is we give the type first, and then we let the editor and the language guide us towards writing the correct program. So it's rather than thinking of types as being the part of the compiler that tells us off when we did it wrong, we think of the types as being the part of the compiler that helps us get to the right program. So types are your research assistants. Types are not your teacher, they're your research assistant. Think of it that way. So I'm going to say to the machine, okay, I've written down the type. Please give me a candidate definition, like a skeleton definition of this function. So I'm using Atom here. You can do this in Emacs or Vim. I think there might even be a VS Code mode these days because that's the new trendiness. I haven't tried it yet. But there's interactive editing modes for various editors. So if I hit Control A for add definition, it will add me candidate definition. So just like you'll have seen this in ML or Haskell, we'll define functions by a collection of recursively defined equations. So it's given us the one recursive, well, it's not recursively defined, the one equation that sets up this function. So this thing on the right here, we'll see a lot of these. I call this a hole. Well, lots of people call it holes. That terminology predates Idris by a long time. So the hole stands for a bit of the program that hasn't yet been written. So holes are perfectly valid bits of syntax. They have types. Essentially what happens when this type checks is this hole becomes a top-level definition, and it has the various names that are in scope. So isString is in scope. And I can check the type of that in Atom, so Control-Alt-T for type. And at the bottom here, it gives me the name in scope and the type of the hole. So that means I can use isString on the right-hand side. So something else I could do is say, okay, I want to inspect isString. I want to see what the possible values of this are. So what this function is going to do is calculate a type based on that boolean, string or nat. So isString implies that if this is true, I'm going to return string. If it's false, I'm going to return nat. So I will say to the machine, okay, I want to look at this string, give me the possibilities. So Control-C for case split gives me the two possibilities for this case. So if this string is false, I guess that means I want a nat. If string is true, I guess that means I want a string. So there we are, that's very exciting. It's a function that calculates a type. Why would I ever want to do that? Well, where do you use types? You use types in types. You can build bigger types out of smaller types. So you can build function types out of individual types. So as another small example of a function that can use this, this is a function that will either calculate the length of a string or double the natural number input, depending on whether this Boolean flag was true. So let's do the same again, add a candidate definition. And if I check the type of this hole now, so this is where first-class types start to actually do things. If I check the type of this hole now, we'll see that what we have, I'll scroll up. We'll see that what we have is something called isString, and then something else, which is, well, the type of X is string or nat isString. I mean, basically, I don't know what the type of X is. The only way I can ever find out anything about the type of X is if I look at this string here. So that's what I'll do. I'll case split on this string again. It's given me two possible cases, right-hand side 1, right-hand side 2. So in this first case, if I check the type of length or double RHS1 again, we should see that it's refined the type of X. So it now knows, because that was string or nat false, it now knows that X must be a nat. And in the other case, it now knows that X must be a string. Okay, so that's like the basics of how you might use a type level function in a type to refine the type of something a little bit. Now this example might seem hilariously contrived, and that's because it is. But you've probably seen functions a bit like this before. If you're looking at this thinking, why would I ever want to do that? Well, there's probably some C programs in the room, and you've seen printf. Printf does exactly this. The only thing is, C compilers tend not to have dependent type systems. So it has to be hard-coded. The check on the format string for printf has to be hard-coded. So if you have first-class types, you can write this as a function without doing anything particularly fancy. So I have this down the bottom here. I'll scroll right down here. We don't see all the details. We see the type of printf is given some string, calculate the type of printf from that string. Now, nobody has objected yet, but I haven't tried any of these programs. So that's sort of like the intro to the idea. Let's at least try printf just to show that it really does something. Oh, I've left my other Idris wrong. Excuse me a moment. So if I check the type of printf with some format string, let's say %s and %d, then it will give me, it needs a string and an int, give me a string and int. So that's a general idea. We can use types, or we can use values that we only find out later on. We only find out when we run the function, or when we evaluate the function, what the types of the rest of the inputs will be. But the machine can do some reasoning about, if you give me this input, that will be the output. Now, what's all this got to do with state machines? So this is just a little example of a pure function. So just to remind you of the picture. No, that's the wrong one. Again. Just to remind you of the picture, I want to represent this state machine as a type program and represent these transitions as types of the actions that we can do on the program. So what we can do, just to do this, yikes. What are we doing wrong? There we go, that's good. So what I'm going to do is write I guess you could call this a domain-specific language, an embedded domain-specific language, an embedded domain-very-specific language for encoding the transitions on a single state machine. So the pattern here, this is a pattern that I use over and over again in independently typed programming. It's kind of the key phrase if you're looking for it, I guess, is index monad. So if you know what I mean by index monad, this will all be pretty clear to you. If not, I'll explain what's happening. So I'm going to define a mini language with the actions that the program can do as a data type. And then, by composing these operations in this data type, we will have an implementation of this stateful system that does the right state transitions. So, we parameterize the type by the return type of the whole operation. So, in our data store example, let's say that we log in, we read the data, and we return the string. So the return type of the whole thing is going to be a string. We also parameterize it by a precondition on the operation. So that's going to be the access state of the data store. So I've defined a data type at the top here. It says, these are the two states of my system, logged out or logged in. So just an enumerated type. Because types are first class, I don't have to do anything fancy. I just put it in the type. Why not? So we've got the state before we run the operation, and then we've got the state after we run the operation. So you can think of this as like a precondition and a postcondition, and you can kind of think of it like a for triple. So it's the operation and its precondition and postcondition are kind of like the for triple that we're doing. We're almost doing separation logic here, but in a very, very simplified way. So to log in, we start in the logged out state, and we end, I claim, in the logged in state. Anyone a bit twitchy about that? Good, good. We'll come back to that. For logging out, we start in the logged in state, we end in the logged out state. And for reading the secret data, we have to be in the logged in state, and we end in the logged in state. So these are the primitive actions on the system. We also need to be able to sequence actions, and maybe we also need to produce values, so without doing any actions. So I've also got a command called pure, which, given some value, doesn't do anything to the system, but it produces something of that. It produces that particular value. Lift I've just added arbitrarily, so I can do arbitrary I/O actions. So I've already broken everything by doing this, but it allows me to write programs that I can test. And finally, we've got a way of binding sequences of actions. So this one is crucial to the whole thing. So it says that if we start in state, if we've got something that gets us from state 1 to state 2, and given that result, we've got something that gets from state 2 to state 3, then we can get from state 1 to state 3. So we can sequence actions. Now, just to see how that works for a simple example, I will write a program on this data store. So you can always look at the types of holes. It's kind of good practice, in fact, when you get a new hole to check its type, just to see how things are going. So the first thing we're going to do with this system is log into it. If we log into it, then remember this is type-driven development, so we look at the types as we go. As we do in action, we have a look and see what state the system is in. So we look at the type of this, and it says, aha, now you're in the logged in state, and you need to get into the logged out state. So now that we're in the logged in state, I can read the secret data. Or I'm going to delete that. Okay. I'll read the secret. And then I could try to return the secret. Is this going to work? Any guesses? No, people shaking their heads. No, it's not going to work. Oh, that's unfortunate. I don't think I can make this error message any bigger. This is a flaw in the atom mode, but I'll tell you what it says. It says it went wrong. Honestly, reading these error messages, that's what that's often all you get out of them. However, it does say, if you look a bit closer, and you have to look very close, it says type mismatch between logged in and logged out. So I promise you that's what it says. What that means is I had to log out before I returned. So, and this says in tiny letters, file loaded successfully. So, some people were not comfortable with that. Why were you comfortable with that?
You can't fail the login.
You can't fail the login. I'm now asserting that login has succeeded. And if you were to write your highly secure data store that way, that's not going to work. That's going to leak essentially. So we need to. The real problem here is that I have claimed that these state transitions go from one state to another, but I'm not in complete control as the programmer, as the user. I'm not in complete control of how these state transitions should work. Something outside is going to have some influence, and that's going to be, did I type in the password correctly? So what we need to do is refine it slightly. So instead of saying, so this is the slightly modified version, and instead of saying that the result type, as the post condition of the operation is just some state that I'm asserting, the result of the operation is going to be calculated, so the real state of the operation is going to be calculated from the result value of the operation. So change the type of store slightly, so it returns some type again, and remember I can give types, I can give them names, so if I give them a name I can use them later on. So I've still got a precondition. I can only run some operation if the store is in a particular state. But then the post condition is going to be calculated from the result of the operation. So it might depend on it, it might not. So if I'm logging out, I claim that's always going to be successful. I always end in the logged out state. I guess that's not necessarily true, but in this system, let's assume it is. But if I'm logging in, then whether login was successful depends on what the system tells me about the result of logging in. So the types of things, I'll start with read secret because it's probably the easiest. Starts in the logged in state, and whatever happens ends in the logged in state. So const is just a function that throws away its second argument. So const is this result type says, okay, it's always going to be the logged in state. So log out is always going to get us from logged in to logged out. And the interesting one is log in, because now, instead of just returning units, it's going to return some value, log in result, I'll defined up here. So OK or bad password. And if that result is OK, then we're logged in. If it's bad password, then we're logged in. So essentially it's saying that we can only find out what the state the system is in by bothering to check the result of login. So let's write this. Do as before. Let's try logging in and check the type of our resulting poll. And it says, well, this is now the type of our system. Oh, notice I'm returning maybe string because I've acknowledged that I might not be able to get access to the super secret data here. So we start in the state of this whole operation now. It's starting in case something of stuff. So essentially, this is saying we don't know what state the system is in now, and we don't know because we didn't check the type of we didn't check the result of logging in. So put res. So if this underscore here, it's just an underscore because I didn't bind the result of that login operation to a variable, so it doesn't have a name. So if I check it now, it should have a name. And the hint here, remember when I showed you length or double, we didn't know what the type of x was because we didn't know what the value of this string was. Here we don't know what state we're in because we don't know what the value of res was. So this is suggesting that what we have to do is check it. So like all good C programmers, we check the result of operations that might fail. Why do people laugh when I say that? So let's check the results. And just like before, I can do a case split on this case file. If it's a pattern, if it's in some position where the syntax is a pattern, I can do a case split in the editor. So if I do a case split on case file, it tells me, okay, there's one case where it's okay, one case where there's a bad password. In the okay case, there we go, we're logged in, we need to get to logged out. And in the bad password case, we are in the logged out state and we need to get to logged out. So I'll just finish this off. Pure nothing. And good, that's I checked. And in the OK case. So now I can read the secrets successfully. I'd better log out. And then I can return. I don't know why this is so sluggish today. I'm probably running some hyper expensive operation in another window like Chrome. And is being remarkably sluggish. Well, it did load. Okay. I'm definitely doing something weird. What do I have to kill? What is disk node D, any Mac fans? And has it ever started running in one of your talks? 388% CPU. I was going to kill it. What could possibly go wrong? Nope, it's a kill all. Like an unkillable process. Just kill all mine. 409, I haven't got that many CPUs. No, that look better. Great. Is software, this serves as a wonderful demonstration of why you should care about not only the results of your programs, but what they do while they're running, and how they affect the state of the outside world. So there you go. Right. Where were we? We just got our secret data. Great. Now, there's something that still is a little bit awkward about this, and that's, imagine if you have lots of secret data to read, and you want to log in and log out lots of times, and they all might fail. So you might end up with a cascading, a cascading case block going very, very far off to the right. And typically it's just the one happy path that you care about. So we want to know, we want to deal with errors when they happen and know you bomb out, but the successful cases we just want to work through. So there's a bit of syntax that Idris provides to make this a bit easier, and here's one I made earlier. So these two programs are equivalent. So what are this first one is syntactic sugar, or this one is syntactic sugar for the one we've just seen. And so the idea is that when we log in, we pattern match on the result and say, right, if the result is okay, we'll carry on running. So this is if you're familiar with Haskell, you'll see the irrefutable patterns in do notation where you match on the result and you just carry on assuming that was the result. But you do need to, so this is what's going on here. We've coded to the happy path down the left here. But after you match on one of these results, you can also say what happens if it goes wrong. What about the alternative patterns? What about the ones that were the default? And so this is a syntax I came up with to help this, inspired by Perl. So that never fails to get a laugh when I say that. I don't know why. Well, all right, I do know why. So you know the syntax in Perl where you open a file, it's open file or die. You familiar with people? So it's a similar sort of idea, except that this thing on the right-hand side has to properly clean up. So if there's some states that you have to clean up the type of Okay, so that's the basic idea. That's the basic programming pattern that I'm going to use, or that I use an awful lot when writing development type programs. Yes.
That was a line break.
What was that?
That was a line break.
Question, what happens on line break? So imagine if I had multiple ways of failing, like not only bad password, I know, bad username. So if there were multiple failure modes, I could add them just like this. And there is an offside rule here. That, if I remember rightly, they have to be lined up, but I might not remember rightly. So again, we can do this sort of thing as long as the whole thing is indented slightly more than the line is. Right. We have an exception. So we
Is it fire alarm?
So, this is a really nice pattern. I use it a lot. So I've used it for things like concurrency, session types, networking, and what you do. I'm sure this is something that everyone really does do here. If you have a pattern that you use a lot, try to abstract it. Try to come up with a way of generalizing it for all of the situations you want to use it. So. So what I would like to do is take this pattern, generalize it, have a general pattern for programming with stateful systems that might go wrong. So I have a fairly long wish list for the kind of descriptive APIs I'd like to give to my stateful systems. So certainly they need to capture the state of the store. Or the store, by analogy, might be a file, or it might be a channel for communicating. It might be a network socket. So I want to capture that sort of thing in the types of the operations. I want to say when the operations are valid. That is, as you've seen, I want to describe the preconditions. And it might be that those preconditions apply to not only one thing, but multiple things at once. So I might have to have 2 logged-in stores for them to communicate with each other, for example. I want to describe how the operations affect the environment. That is, I want to give post-conditions on operations that might be influenced by what's happening to the world. I wanted to interoperate. So, big problem with this system I've shown you is that I called it a domain very specific language, by which I meant I have given you a very small set of operations and no more. So I can't add new things to this system without changing the definition of my embedded DSL. Which I really don't want to do that. So I have to re-implement it every time for every kind of stateful system. I can't do fairly common things like have a data store, read the results and store it in a file. Or I can't even have multiple data stores. I can't connect and disconnect at will. So I want to be able to pull all of these stateful APIs together and have them interoperate with each other. This is crucial. I want them to be readable. The types may be very expressive, but I also want you to be able to look at those types and say, yeah, after I know what a couple of functions do at least, yeah, I know what that operation does. So I don't want to hide any necessary complexity, but I also don't want to have any unnecessary complexity visible, because programming is complicated enough already. So let's try to make the types descriptive, but also not overly descriptive, not overly detailed. Also, this is the challenge. I also want to have helpful error messages. I don't want you to have a look at a big load of type and just say it went wrong. I want the error messages to give at least some kind of clue as to what went wrong and what you have to do to fix it. So this is something that's been bothering me for ages. This sort of being able to take these embedded DSLs, index monads, whatever you want to call it, whatever direction you want to peer at this at. And I've been bothered about how to put lots of these systems together, how to build larger systems by composing lots of index monads. So if you are Haskell programmers, I guess you're familiar with monad transformers. So this is how you might compose lots of monads in Haskell. Does anybody fancy writing an index monad transformer library? So everyone's shaking their head, but Miles is looking at me thinking, oh yeah. No, okay, even Miles says no. There we go. No one wants to write an index monad transformer library. So let's see if we can find a way of composing these systems that's a little bit nicer. And there's quite a lot of there's a lot of interesting things have been done over the last, I don't know, well, over the history of computer science on this kind of problem. So if you look at things like separation logic, this is kind of the sort of thing separation logic does. So this is if people who've played around with or used Coq might be familiar with the Why Not library. So Why Not is a library in Coq for proving the correctness of imperative programs, essentially based on Paul logic. I'm happy to admit that it took me a very long time to notice that Why Not was Tony backwards, so I assumed it's named after Tony Hawk. So index monads, linear types, all of these things have a relationship to what I'm trying to do here. So looking at how all these ideas work, and just seeing what bits we can pull out to make a nice, hopefully readable library for Idris stateful programs. So this is what we've come up with. So there is a type for all of the stateful programs that we're going to be writing in Idris. So ST is the type of stateful programs. ST for I don't know, state transition, state transform. I actually call it ST because why not call it? It's a comparable thing, ST. So just like our data store, it's parameterized over a few things. So first thing I'll point out is this type. This is the type that's produced by the sequence of stateful operations. We also have a list of state transitions. So before we had the preconditions and the postconditions. So this list of actions is capturing that idea of precondition and postcondition just in one parameter. So it's a list of state transitions on all the different state variables that the system can have. Additionally, you can add new states and remove states. So it's a little bit more than what we've just seen, but essentially it boils down to state transitions on types. And this last thing I haven't pointed out yet is this M is the underlying context in which we actually run these programs. Because after I've proved my programs correct, I've proved that they follow the right state transitions, I would like to understand how they work. And that involves explaining how they work in some particular computation context. The M is suggestive of something. It doesn't have to be a monad. This talk contains the word monad exactly twice from this point on. So in fact 0 times from this point on. So it's really about the context in which we're running things. And I've realised I've got myself into a corner because I wanted to say the M word there. It doesn't have to be a monad, sorry. It just usually is. So there's an underlying context in which we're running these programs. So let's go back to the data store. We'll do the same thing. We'll write that data store program again, but in the context of ST, and then we'll see what else we can do. So what the data store program looks like. So the general idea is that we'll say what interfaces the program is allowed to use. So this is an interface constraint. If you speak Haskell, this is like a type class. If you speak ML, this is a bit like a module. It's actually more like a module than a type class, but just think of it the way you want to think of it, it doesn't really matter. All it's saying is that there is an interface that we're working with, and we say in the type what interface we're working with. So this program is allowed to do things that are console I/O related. It's allowed to do things that are data store related. So that's the M that is the context in which we're running this program. So it's returning the unit. So in this case, I'm printing rather than returning the secret, I'm printing the secret or printing an error. And then this is our list of actions. So the list of actions as viewed from the outside in this program is that at the end, we'll be in the same state as we started in. So if there's nothing in that list, it means that at the end, the state is the same at the beginning, so essentially nothing happened. Things did happen internally, but from outside, nothing happened. So basically means that if we create new states, if we do straight transitions, whatever we do is okay as long as we clean up after ourselves. And by the way, people often say, when I say people often say, I think I tend to be referring to comments on Reddit or Happy News or that sort of thing, but that's what people say, isn't it? So people often say that if you're programming with dependent types, you have to write type annotations everywhere. And this sort of comment really irritates me because you don't. You have to write top-level type annotation. Kind of important to say what the program's going to do, but that's all. So this program, this data store program, I'm going to claim that it's readable once you've got a grip on the syntax. So, depending on your background, you might find different bits differently readable. But once you've got the hang of the syntax, it's just saying what's going on. The only type declaration is this one that says, we return a unit, and by the way, we clean up after ourselves. And these are the interfaces we're allowed to use. Otherwise, no more type annotations. So it's completely full of dependent types, but they're all being inferred because that's what we do. So the only difference between this program and the earlier one, apart from that, is that I have to connect to the store and I have to disconnect at the end. So I have to explicitly say I'm talking to the store, and I have to explicitly say I'm finished with it. This means that I can talk to more than once. I can connect to multiple stores. That will show up in time. So now you've seen how what the program looks like. I'll go a bit deeper into what the types of the individual operations are, and you'll see how they match, or how they map to what we've seen earlier. So, essentially the general idea, we're going to, just to start looking at the types, we're going to define interfaces for the operations. So the interface says what operations are permitted in a particular context. And then, when it comes to running the program, we'll implement that interface in a specific context. So we're going to implement an interface for the data store. So this is a way of introducing an interface declaration, and then we're going to implement this one for I/O. So this is going to be the simplest possible implementation, where it prompts you for a password, you have to type in the right password, and it prints the result if successful. So the operations themselves. So to read the secret, just to start with the simplest one, this says I'll work in some context M, I'll return a string, and the one action I have is the existence of a store that is logged in. So this triple colon is it's actually an Idris function. It's intended to say this is the type of the resource we're working with at this particular point in the program. So there's a variable called store. At this particular point in the program, its type is a data store that's logged in. So store logged in is a type, and store is we can think of as our variable that we'll use to refer to that store. So we start and end in the logged in state. Logging out is a little bit more tricky. So logging out, we have a store, and then we write the transition. So again, ordinary Idris functions, quite heavily overloaded. We'll let the machine deal with that. And so we can write down the transitions explicitly. So logging out is a transition on the store from a store that's logged in to a store that's logged out. Logging in, well, this isn't quite right. This is logging in without checking for success. So again, we need that trick of having the result state depend on the type of the result of the operation. So just like before, we say, right, the store starts in the logged out state, and the transition goes to a function of the result of the operation, which is exactly the same as before. The type of the store is calculated from this result. It's okay, we're logged in, bad password, we're logged out. So what's happening with this ST type is we are able to say that kind of thing, the preconditions and postconditions that we had in our state transition systems before. It's just that now we refer to each one by some variable, and I can add and remove those variables as needed. So how do we add and remove them? Well, we can also say, I would like to add a variable now, please. So connect says, I would like to add a variable now, please, of type store logged out. It'll return some variable. So notice we've separated the concept of a variable and the state of that variable. So everything here, everything in the system is of type var, and then these lists tell you what the current state of that var is. Okay, so ST itself, I'll say a little bit about this. It's a type level function, and it turns into a lower level thing called strans, which looks even more like what we've seen before. So remember before we had action that returned a type, it had the access status, then it had a function to calculate the new access status. Well, strans, that's ST, what ST is underneath, exactly the same thing. It's just that these resources are lists of resources, and they can grow and shrink as needed. So rather than go into the technical details of what goes on there, so there is a draft paper about this, you can read all the technical details. It's essentially the well-typed interpreter pattern. If you know anything about the well-typed interpreter pattern, it's like defining a language with its types, with its explicit types in the type of its representation, and an interpreter for it. So it is in fact completely conventional for how this is implemented. So I don't want to go into any more detail here. Do read that in the draft paper. What I would like to do though is show a more meaningful example of this in action. So I'll skip ahead to. Actually, no, I will show you the data store in action just to show how things work, and then go straight to the thing. So this is the program we've just seen in slides. So defining an interface, and I say just abstractly the store is represented by some abstract type. So these are the operations that I've just seen defined. This is the program we've just seen. But what we need to say a bit more about is how to implement this thing. So underneath, there has to be a way of reading and writing the variables, doing the transitions. So in our implementation, so this is the implementation of the data store where I say, okay, it's going to be explicitly represented by a string. So this is right here. But our secret data is merely some string. In fact, this one is self-describing secret data. So there's our secret data. And to log in, I have to explain how to log in this IO context. So I have to type in the right password. So I have a prompt for a password, and then if I type the right one, it's okay. And then to read the secret, all I have to do is read the store. When we implement this, so this implementation of read secret, we are working under the assumption that the types have got us into a stage where it's okay to read the secret. So all we do is read it. And eventually, to run one of these programs, there we are. That's what we do. We run that program in the context that we happen to be in. I will run it. It's amusing how when you plug in the projector into a Mac, you never know what resolution you're going to get. It's changed in the time we ran. So you need an entropy be a random number generator. There you have it. So it's called login behind you, I think. I can compile and run things with this call and exec command. It asks me for a password. I'll give it the wrong password. Failed. I'll give it the right password. Morning to present. So I've won. So it's given me the secret data. Okay. So all I did was say this is how you run it in the IO context. Now, slightly more exciting example is how to deal with concurrent programs. So, I've got about, 5 minutes for this? Probably leave time for questions. Six or 7 minutes. I'll use those extra 1 or 2 minutes wisely. The way I'm going to do concurrency. So I'm going to show how this idea of representing states makes concurrent programs, well-typed concurrent programs possible. So the Idris runtime supports message passing concurrency. So you spawn a new thread, there are lots of heaps, those heaps can send messages, each process has its own heap, or each thread has its own heap, and you can send messages to threads directly. So a process can create a channel by either connecting to an existing process or listening for connections from another process. So it's kind of like a CSP sort of message passing. And once you've got a channel, you can send and receive messages on the channel. So you get this kind of programming pattern where you've got a couple of concurrent processes. Maybe you start up a process to act as a server, which is just dealing with one specific task. So this particular example, I have a process whose one job is to add numbers. So I can send a message to the server saying, add 2 numbers, that can send a message back saying, okay, 2 + 3 is 5, and carry on that way. Now, the sorts of things that can go, well, all kinds of things can go wrong once you start talking with concurrent programming. So you might send the wrong type to a process. You have to explain how the types match up between processes. You might send messages in the wrong order. So, if this thing adds 2 numbers and then adder sends 2 results, and it's not expecting that result, and the protocol gets in a mess, and you end up deadlocking. So you want to be careful about how the order you send messages in and the types of the messages you send. So this sounds a bit like a job for session types. This idea of session types that Cohen Honda and others have developed over the last 20 odd years is giving types to channels that you're communicating on. So the state of a channel is what's expected to happen next on that channel. So a session type is something that describes the state of a communication channel, whether I'm about to send a message on it, whether I'm about to receive a message on it, what the type of that message should be. So essentially it's tracking the expected sequence of communications on the channel. So anytime we're tracking expected sequences of things, we have a protocol that we need to follow. This is something that ST can do. This ST type can. We can create threads. We can create channels for communicating between threads. Give types of channels for tracking states, and it's all physical. So let's just see how that works. I'll show you in action. So I'll define for this adder thing. I'll define a protocol that says, well, we'll send a request of this command type. So the only command I have available here is adding two numbers. And if the command is add, the server will send back a number, and then we're done. So we can view that protocol from two directions, either as the client or the server. If we're the client, then we have to connect to a server, send a request, and get a response. If we're the server, we have to listen for a message, receive a request, send a response. So I've written this as an ST program that says, given that protocol, calculate me the actions that are appropriate for being the sender. And rather than going through this bit by bit, it's much easier if you're looking at an Idris program trying to work out what it does. I find it really useful to just comment out a chunk of the program, replace that chunk with a hole, and look at the type of a hole, and the hole will tell you where you are, what's going on at this point. It would be lovely if the IDE had support to do this without me editing, but it probably doesn't. So if I look at the type of food, it tells me all the things I have. But the interesting thing is that I've got a channel, so I've created a channel, and it says here, chan is a channel, and it's expecting to receive a command, and then do some stuff. But we'll worry about the stuff it's going to do next once we've received the command. So let's put that in here. So if I receive something, oh, what? I don't usually use atoms, so it surprises me sometimes. So if I receive something on that channel, check the type of the hole again, it says, aha, now, as the server, what you do depends on what the command was. So if the command was add, you need to serve a NAT. So let's go into this case here. Again, I'll do the same thing. So if I've received the command and checked that it's add, it should tell me that what I need to do next is send back a NAT. So yeah, so it now says, right, at this stage, we've received the command, we've looked at it, and it says, now you have to send a NAT back, and then this continuation of the channel is, now you're done. So once I've sent it, I'm done at this point, so it says, right, channel's done. When the channel's done, it's at the end, you'll notice that you have to squint a bit to look at these types, but it'll kind of appear and see what's going on. You'll notice that chan doesn't appear in this, so I have to get rid of it somehow. So I'll get rid of it by closing it, and then we're done. So as far as reading those types goes, you do have to know which bit of the types you're looking at. But if you know which bits of the types you're looking at, you can track the protocol as you work through the program. So, and then this program itself, all you see in this program is, you have to be the server for adder, and then this is listening for a connection, and then sending a response if you get a message. Slightly more excitingly, you might have multiple commands. So this thing is this protocol can either add two numbers or append two strings. So the thing it's sending back is different depending on the message it gets. So when we write the server, we have to send a different thing back depending on the message it gets. And just to finish, I have a little program that does all sorts of addition and gluing strings together concurrently, just because it can, by calling this server. And I guess I could run it. Compile the right file. Arrow started. It's very hard to see that this is concurrency in action, but the fact that it's compiling and running, you can see it's logging that it started the server, counting requests and so on. Okay, so That's just to show that this, Sam was waving at me like he wants me to shut up. I'll shut up in a minute, I promise. This is just to show that this idea of ST, this ST library, even though it's a fairly simple way of, I claim it's a simple way of describing APIs, and you can see exactly what those transitions are. It does scale up to things like session types. You can write concurrent programs, track the state, and even compute the sequence of states that you want to work through as type level functions. So, just to finish, we'll get to the, just to summarise what I've talked about, having first-class types, I think when the essence of that idea is a really simple one. It's just that you calculate types from functions. That's all there is to it. But it gives you all sorts of interesting things you can do. Particularly, you can express state transitions into types. So, in the end, we can express these communication protocols, so these increasingly complicated communication protocols, that getting concurrent programs working in a nice synchronized way in the type. So, not just what you're supposed to do, but when you're supposed to do it. So, leave the room is one thing you're supposed to do it. When you're supposed to do it is when the fire alarm goes off. This sort of thing you can express as part of the protocol. So, ST as a library is just there to support these state transition systems. It's a pattern that I use all the time. I've seen it used a lot, certainly in Haskell programs with index finance in particular. So it's something that's worth thinking about how to do nicely and reusably. So ST is there to do it nicely and reusably. We can do session types with it. So I have another example of network protocols. So I guess I can show you the state machine. So this sort of state machine of working with networks on. So every program, I think, every realistic program, in some sense, is a hierarchy of state transition systems. So being able to express those state transition systems in the types, I claim, is going to help us write programs that actually work, do the right thing at the right time. Okay, I'll stop there. Thank you very much for your attention.
I was expecting for these state machines, you can actually represent them as index code data. For any reason down?
Indexed code data. Maybe I'll have to think about that. I mean, one thing that I haven't captured here, and I haven't really talked about, is how you do long-running systems. So things that run forever, moving from one stage to the next as we go, and just sort of waiting for it to come along. So that's a good point. I'm going to have to think about that. Is there any reason I don't? I haven't done it yet, and I haven't thought about what could possibly go wrong. You may very well have a very good point. Thank you.
From a sort of implementation point of view, I think this looks quite similar to your earlier effect stuff.
Very, yes.
Does it completely subsume it, or is it a specialization?
It completely subsumes it, yes. So the effects library has a number of irritating problems. So it doesn't, the most important one for me is it doesn't allow you to express when it's okay to create and destroy things. And so you can end up doing some really ugly stuff when creating and destroying things just to make it work at all. And the other thing it can't do is you can't implement effects in terms of other effects. So I didn't show this in this talk, but you can implement a state machine using a combination of other state machines. So I'll just put this on the screen rather than talk about it. I have an implementation of Turtle Graphics, for example, that uses the SDL API as a state machine. So the state machine there is, did you successfully open a window? And then, okay, I want to implement Turtle Graphics, but I just want to talk about the API without talking about SDL. But then when it comes to implementing it, I might want to implement it in terms of that state. Anyway, it's completely impossible to get that library. Whereas here, I'd say, okay, a turtle state is a composition of all of these other states. That's, by the way, why I call it state machines all the way down.
One more question.
So how do you make sure your resources don't escape the scope? Like in this source window example, for example, if I write the window to an IRF or something.
That's a really long question to answer, and it took quite some time to figure out how to do it properly. So perhaps I should show you afterwards. But it's the time to try to capture when it's okay to look at a state, when it's okay to read a state, when it's okay to write a state. So you saw that this thing was these types are called state string rather than just string. So the fact that it's a state means that you can only use it in certain places, and the implementation is quite careful about when you're allowed to do that. But that's a whole can of worms that's a difficult talk, but I'll show you. That's everybody.